Welcome to AI Paper Podcasts, where we dive into the research that's really moving the needle in AI. We know you're busy, so let's jump straight in. Today, we're tackling a huge problem: catastrophic forgetting in LLMs.
Yeah, it's arguably the biggest roadblock to building truly adaptive learning AI systems. You teach it something new, and poof, it overwrites what it knew before.
Yeah.
It's this constant battle.
Exactly. But the paper we're looking at today, Continual Learning via Sparse Memory Fine-Tuning. This is from Jesse Lin, and the teams at Metafair and UC Berkeley. It offers a potentially game-changing approach.
It really does. Their core idea is pretty insightful. The reason models forget so badly is that the parameters, the things that store knowledge, are shared too densely across everything the model learns. It causes this massive interference.
Right, so instead of trying to just tweak that dense setup, they propose something different: sparse memory fine-tuning, or SMFT.
And SMFT builds on these specific memory layer architectures that are already sparse in how they access information.
Yeah.
But the key innovation is how they update it.
Okay, so what's the trick?
They use a ranking score, actually inspired by the classic TF-IDF you see in search engines, to figure out which few memory slots are most activated by the new information, relative to how often those slots were used during general pre-training.
TF-IDF. Okay, interesting. So find the slots that are important now but weren't, super critical for general knowledge before.
Precisely. And they only update those specific, highly ranked slots. Maybe just the top 2 of them.
And does it work? What's the headline result?
Okay, get this. On a benchmark measuring forgetting, like NaturalQuestions F1, standard full fine-tuning just cratered performance dropped 89%. Even LoRA, which is designed to be safer, dropped 71%.
Wow, okay. That's catastrophic, literally.
Right, but sparse memory fine-tuning, achieving the same level of learning on the new task, only caused an 11% drop.
11%? That's a massive difference. That feels like breaking the trade-off.
It really suggests sparsity is a much more promising path forward than we perhaps realized.
Okay, so that 11% number is what we need to unpack. Our mission today is to dig into how SMFT uses these sparse architectures, nail down that TF-IDF mechanism, and understand why this specific technique seems to offer a much, much better balance between learning new things and not forgetting old ones. So maybe let's start with the why. Why is continual learning so critical for the LLMs we're trying to build today?
Well, think about practical applications. We want models that can remember user preferences, right? Or learn from feedback when they make a mistake, or even acquire entirely new skills over time without needing a full retraining cycle.
Which is basically impossible right now because of this forgetting issue.
Exactly. It's this problem called catastrophic forgetting, and honestly, it's been plaguing neural networks since the late 80s. The root cause hasn't really changed.
Yeah.
You're optimizing the same set of parameters over the model's entire life. Every new update risks messing up the weights that hold on to older knowledge.
Okay, so people have obviously tried to fix this before. What about the traditional approaches, like replay methods?
Yeah, replay is the intuitive one. Just mix old data in with the new data when you're fine-tuning. But it's incredibly inefficient. Think about the scale of data modern LLMs are pre-trained on and then instruction-tuned and aligned.
You can't just keep storing and replaying all that data forever.
No way. It just doesn't scale. So then you have regularization methods like EWC, elastic weight consolidation, or just KL penalties.
Right. Those try to sort of anchor the weights, stop them from changing too much from their original pre-trained state.
Yeah, they restrict the updates, but they don't fundamentally solve the interference problem because the parameters are still shared. They just make it harder to learn the new stuff effectively sometimes.
And then there are methods like LoRA, the low-rank adaptation approach. That's been really popular.
It has, and LoRA definitely causes less forgetting than just fine-tuning everything. But it comes with its own trade-off. Because you're only adding a small number of new parameters, its capacity to learn genuinely new knowledge is limited. Other research pointed this out too. Less forgetting, yes, but also you just learn less.
So it sounds like the existing methods either don't scale, don't fully solve the interference, or limit how much new stuff you can actually learn.
Pretty much. That's the landscape SMFT is trying to improve upon.
Okay, so if capacity was an issue for LoRA, the SMFT authors needed an architecture that had lots of capacity but could be updated very precisely. This brings us to the memory layer architecture they build on. What is that exactly?
Right. So this memory layer idea comes from some earlier work. It essentially replaces some of the standard feed-forward network layers, the FFNs, in the transformer blocks.
Instead of a dense FFN layer, you have what? A big database?
Sort of, yeah. It introduces this large trainable pool of memory keys and values. Think of it like a huge bank of potential storage slots. The paper mentions sizes from maybe 1 million up to 100 million key value pairs.
Okay, that's massive. But the key is how it's accessed, right? You mentioned sparsity. It doesn't use all 100 million slots at once.
Definitely not. That's the crucial part. It's designed to be sparse during the forward pass. When the model processes input, a query is generated, and it only retrieves information from a very small subset of those memory slots. Like the top K equals 32 keys per memory head in their setup.
32 out of potentially millions.
Exactly. So for their 1.3 billion parameter-based model, a standard FFN might have, say, 50 million parameters all firing. The memory layer might have tens of millions of total parameters in its pool, but during any single computation, only maybe 30,000 or so are actually active. It's a tiny fraction.
That gives you incredibly fine-grained control. It's not like activating a whole block of parameters. It's like picking out individual little nuggets of information.
Precisely. Much more granular than, say, mixture of experts models where you're still activating a relatively large expert network. This inherent sparsity in access is the foundation SMFT builds on.
Okay, foundation laid. Sparse access via memory layers. But here's the kicker you mentioned earlier. The paper found that just fine-tuning all the access memory slots, even though it was only 32 per head, still caused catastrophic forgetting. Why?
Yeah, that's a really critical point. It turns out that even among those sparsely accessed memory indices, some are probably doing double duty. They might store information about, say, basic grammar or common facts, things learned during pre-training that are needed for general language understanding.
So if you just overwrite those slots with new information, even if they were accessed for the new tasks, you're still damaging the model's general abilities.
Exactly. So the intuition had to be. We can't just update everything that's accessed. We need to figure out which access slots are specifically important for the new piece of knowledge we're trying to teach the model right now.
Okay, so filtering the access slots down even further. How on earth do you identify the important for the new stuff slots mathematically?
This is where they had that clever idea of borrowing from classical information retrieval. TF-IDF. Term frequency inverse document frequency.
Right, TF-IDF. I remember that from like basic search engine stuff. How does that map onto memory slots in a neural network?
It's a neat mapping. They treat each memory index, each specific key value slot as a term. For a given batch of new training data, the term frequency, or TF for index I, is simply how many times that index I gets accessed by the queries generated from that batch.
Okay, simple enough. More accesses on this batch means higher TF. What about the IDF part? Inverse document frequency. That measures rarity, right?
Right. And this is key for avoiding those general purpose slots. They calculated the IDF by looking at how often each memory index was accessed across a background corpus. Specifically, they used 1,000 random batches of data from the DCLM dataset that's data similar to what the base Llama model was pre-trained on.
Okay. So the DCLM data represents general knowledge or pre-training usage. If a memory slot was accessed all the time during pre-training, high document frequency on DCLM, its IDF score will be low.
Exactly. The IDF term effectively downweights indices that are commonly used, the ones likely holding general syntactic or semantic knowledge.
So the combined TF-IDF score ranks the access memory indices. High DCIDF means an index is frequently accessed for the specific new batch, high TF, and it was relatively infrequently accessed during general pre-training, high IDF.
You got it. That score pinpoints the memory slots most likely dedicated to the new information, not just generic language processing.
Genius. Okay, so they have this rank list of access memory indices. What's the final update step? Do they just update the single top-ranked one?
They update the top T indices where in a hyperparameter they can tune. So maybe the top 500 or top 10,000 depending on the task. And critically, during the backward pass, when gradients are calculated, they stop the gradient for all memory parameters except for the values associated with those top TF-IDF ranked indices.
Wow, so the forward pass uses all access indices to get the best prediction, but the learning signal, the gradient, only flows back to modify that tiny dynamically selected top T subset.
Precisely. It's like putting a dynamic, highly selective write lock on almost the entire memory, based purely on this relevant score calculated for the current data. It ensures the update is minimal and really targeted.
Okay, the mechanism is clever. TF, IDF to find the specific slots, stop gradient to update only those. Now, the big question, does this actually work in practice? Let's look at the experiments, starting with that really tough small data scenario.
Right, this is the fact learning task. They took a 1.3 billion parameter base model and tried to teach it 1,000 new facts from the Trivia QA dataset. The setup involved paraphrasing each fact multiple times within a batch, simulating trying to quickly integrate a very narrow piece of information.
And you said this is tough because the risk of the model just collapsing or forgetting everything else is super high with such narrow data.
Extremely high. So they measured learning on the Trivia QA facts themselves using F1 score. And crucially, they measured forgetting on held-out benchmarks. NaturalQuestions F1 for general QA ability and GSM-8K negative log likelihood for reasoning.
Okay, NQF1 makes sense, but GSM-8K, NLL, negative log likelihood, what does that tell us simply?
Lower NLL is better. It essentially measures how confident and accurate the model is on math word problems it saw during pre-training. A high NLL means the model has become very uncertain or just plain wrong on tasks it used to be good at, is forgotten how to reason effectively.
Got it. So the results. You gave us the headline NQF1 drops earlier, which were dramatic. Remind us again.
Yeah, the comparison was stark. Full fine-tuning just wrecked the NQ performance, an 89% drop. LoRA was better, but still terrible, a 71% drop. But SMFT, using a carefully chosen update size, T500 was best here, only showed an 11% drop in NQF1.
11%. It basically learned the new facts just as well as the others, but kept almost all of its previous QA ability intact.
Exactly. Minimal interference, even in this worst-case scenario for forgetting.
Okay, that's compelling for single isolated facts. What about a more continuous stream of information? They also tested this on document question answering, right?
They did. They set up a task using streams of document paragraphs related to 100 questions from the simple QA dataset. This involves richer, more diverse data per batch.
Did the baseline methods do better here with richer data?
They did perform better than in the super sparse fact learning regime, which makes sense. More diverse data helps mitigate forgetting somewhat. But both full fine-tuning and LoRA still showed significant forgetting on the held-out benchmarks.
And SMFT. Did it still maintain its advantage?
Yes. They use a larger update size, T10,000 here, because each batch contained more information. And SMFT, again, achieved the same level of performance on the target simple QA task, but with substantially less forgetting compared to the others.
This really points towards that concept you mentioned, the Pareto frontier. Can you explain that trade-off again?
Sure. It's this fundamental tension in continual learning. You want high learning rates, lots of updates to learn new things quickly, maximize learning. But you also want to change the model as little as possible from its pre-trained state to avoid forgetting, minimize forgetting.
You can't usually have both. Pushing one hurts the other.
Right. But when they swept the hyperparameters for all three methods, full FT, LoRA, and SMFT, they found that SMFT consistently offered a better deal. For any given level of performance achieved on the new task, SMFT always resulted in less forgetting than the other methods. It Pareto dominates.
So across the board, you get more learning bang for your forgetting buck, so to speak.
Exactly. It shifts the entire achievable trade-off curve upwards.
That's powerful. Let's dig even deeper with the ablation studies. What did they find when they messed with the SMFT mechanism itself? Like, what if they took out the crucial IDF part of the ranking?
Great question. They ran a couple of key ablations. First, just confirming that naive fine-tuning updating all K32 access memory locations still leads to catastrophic forgetting. That reinforces the point. Sparse access isn't enough. You need sparse updates.
Okay, so the targeted update is essential. What about TF-only ranking? Just updating the tool most frequently accessed slots in the current batch, ignoring the background pre-training frequency.
That's the crucial comparison. TF-only ranking learned the new facts pretty much just as well as TF-IDF. However, it caused significantly more forgetting.
So the IDF part is critical.
Absolutely critical. It's the IDF term, the one that penalizes frequently used pre-training indices that successfully protects the model's general knowledge. Without it, you end up overwriting important foundational stuff, even if it happens to be accessed by the new task, too.
It acts like a shield for generality. And they also checked the background corpus choice for IDF, right? Using the DCLM pre-training data versus, say, the Trivia QA training data itself.
Yes, and using the DCLM samples worked much better. Using the target tasks data, like Trivia QA for IDF, led to worse forgetting. It makes sense. Comparing against the DCLM data directly helps preserve the knowledge gained specifically during pre-training.
Okay, the mechanism seems robust. Did they look qualitatively at which memory slots TF-IDF was actually selecting? Did it make intuitive sense?
They did, and this part is fascinating. They identified what they called a core set of memory indices. These were the indices consistently accessed across different paraphrases of the same fact in the question itself. This core set represents the pure semantic essence of the fact.
And this core set was small.
Relatively small, yeah. Typically around 100 to 500 indices. And the really cool finding was that the indices selected for update by the TF-IDF ranking showed a very strong overlap with this semantic core set.
So the TF-IDF mechanism wasn't just picking random slots. It was genuinely zeroing in on the memory locations that seemed to store the actual meaning of the new fact.
Exactly. They even showed examples where the highly ranked indices corresponded directly to entity boundaries in the text, like the memory slots activated specifically for names like Michelle Smith de Bruin or Walter Hagen in the facts being learned.
That's compelling evidence that the mechanism is working as intended, targeting the specific storage locations for new knowledge while leaving the general machinery untouched.
It really seems to be the case.
Okay, so wrapping this up. This paper makes a really strong data-backed argument that targeted sparsity, enabled by these memory layer architectures and this clever TF-IDF masking, is a key breakthrough for tackling catastrophic forgetting.
I think so. For simple fact learning, retrieval augmented generation, RAG, is often the go-to solution right now. Just look it up externally.
Right, don't try to bake it into the parameters if you don't have to.
Exactly. But this work, SMFT, opens the door for applications where RAG just isn't suitable. Think about learning complex skills.
Yeah, you can't just retrieve how to reason better or how to write more efficient code based on yesterday's mistake. That needs to be integrated into the model's parameters.
Precisely. This could enable language model agents to continually improve their coding abilities, refine complex reasoning strategies, or distill lessons from intricate feedback loops, things that have to become part of the model itself. SMFT offers a concrete mechanism for doing that without breaking everything else.
That really does paint a picture of more adaptive, genuinely lifelong learning AI. Okay, so since this targeted sparsity in the update seems to be the secret sauce here, let me leave you, our listener, with a final thought to chew on.
Uh-oh.
The memory layer architecture was clearly important here. It provided the addressable sparse structure they needed. But the core principle is dynamic sparse updates ranked by relevance. How might we take that core principle and apply it effectively within standard, dense transformer architectures without needing these specialized memory layers? Could we achieve similar gains in continual learning for any LLM?
That is definitely the multi-million-dollar question, isn't it? Figuring out how to get that kind of targeted dynamic sparsity without the architectural scaffolding of memory layer, that's likely the next big frontier here. It's a huge challenge, but the potential payoff is enormous.
A challenge for future research and hopefully future AI paper podcasts. Thanks for digging into sparse memory fine-tuning with us today.